In this part 2 video, we're looking at 2 more examples of stoichiometric problems that involve gases. I would love to go back to around the time of 1783, at least briefly, and watch Jacques Charles, of Charles' law fame, try to inflate a balloon with hydrogen gas. Well, and apparently he was able to do this and actually fly in the balloon. So let us say he needed to inflate the balloon with approximately 31,000 liters of hydrogen gas. And he did this by reacting metallic iron in the presence of dilute hydrochloric acid. Of course, it would have to be excess hydrochloric acid. What mass of iron filings or metallic iron would he need to produce this volume of gas? And we'll assume this reaction was done in the summertime. So let's say the temperature was 30 degrees Celsius and atmospheric pressure was about 745 millimeters of mercury. Again, this is typical stoichiometry. So here's our balanced equation. What do we know? We know what volume of gas that we're trying to produce. We're trying to determine what mass of iron in kilograms would be required. And we also know the temperature and pressure conditions. So a word of caution, anytime that you're using the ideal gas law equation and the ideal gas law constant, you need to convert the temperature to Kelvin. The pressure must also be in bar, given that the original pressure was given in millimeters of mercury. I'm doing this conversion. Now, just to unpack that a bit, this is 745 millimeters of mercury multiplied by the conversion factor 1 bar per 750.1 millimeters of mercury. Going further then, I'm using my unit plan. So I'm trying to determine a certain volume of hydrogen gas in liters. If I know what volume I want to produce, I can calculate the amount in moles of hydrogen gas that are required. I make use of this modified ideal gas law equation. If I know the amount of hydrogen gas in moles, I can calculate using the balanced equation the amount of iron that would be required, and then finally the mass of the iron that's required. So here is the actual working. So of course the volume of hydrogen gas multiplied by the modified ideal gas law equation multiplied by the stoichiometric coefficients in the balanced equation. Of course, this is very simple, 1 to 1, and then multiplied by the molar mass for iron. So we end up with 68,600 grams, and this is in part why you were asked to calculate in kilograms. So now we convert to kilograms by dividing by 1,000. So 2 examples, quite similar. I'm hoping you're getting the idea that these problems really are no more challenging than any other stoichiometric problem. But we need to do one more. And that's because this problem is actually a tad more challenging and has relevance to a particular experiment that you're going to do in the lab. Because in the lab, and also included here, is you see that we're going to collect the gas by the displacement of water. This is a common way to collect a gas. You need to be comfortable with the parlance or the jargon. So it says here the oxygen gas was produced and was collected by the displacement of water. Sometimes we say that the oxygen gas was produced over water. All right, so it's bubbled through water. The temperature, 22 degrees Celsius. The pressure, 754 torr. The volume of gas was collected is given. And what we're trying to find out is, once again, what mass of the original reactant is required. Now, of course, all 3 examples are similar in this fashion, but do realize that you could be given the mass of a particular reactant and you have to calculate the volume of gas that be produced. It's a similar sort of set of calculations. So let's take a look about this displacement of water and how this all works. So here's a diagram representing this particular reaction. We have the potassium chlorate at the bottom of let's say a test tube. It's being heated. It's being heated in the presence of a catalyst, manganese 4 oxide. Any gas that's produced will travel through the tube, will bubble through water. Imagine that initially this tube would be completely filled with water, and then as the gas is being produced, the water is being displaced. And we can actually determine what the final volume of water is here, and therefore know what volume of gas is generated. Understand that any time that a gas is collected by the displacement of water, The headspace here above the water will include the gas that's being generated, but also some water molecules that have evaporated. So gaseous water. And we need to know what is the pressure of that gaseous water. Fortunately, that pressure only depends on temperature. So here we have a chart, more information than we actually need, but at a temperature of 22 degrees Celsius, the vapor pressure of water, as I say, is a constant, is a known, 19.8 torr. This vapor pressure only depends on the temperature. Let's see what other information we have. So we know the volume of gas in liters that we're trying to generate. We're trying to find out what mass in grams of potassium chloride are required. The volume that was generated is 0.650 liters. The temperature was 22 degrees Celsius, which corresponds to 295 Kelvin. The total pressure in this container is 754 torr, and it's often fairly easy to measure the total pressure, and therefore, in a sense, understanding the effect of partial pressures and that water is contributing a certain portion of that 754, we can calculate what is the pressure due to oxygen gas alone. So the pressure due to oxygen gas alone will be 754 torr minus this 19.8 torr, which gives us this 734.2 torr. Of course, once we have the pressure in torr, again, working with the ideal gas law equation plus the ideal gas law constant, we need to convert this to bar. The actual conversion looked like this, 734.2 torr times 1 bar over 750.1 torr. All right, so that's just an abbreviated conversion. Now, let's look at our unit plan. We're trying to generate a certain volume of oxygen gas in liters. This corresponds to a certain amount based on our rearranged ideal gas law equation. Of course, once we know the amount of oxygen in moles, we can determine the amount of potassium chloride, and then finally the mass of potassium chloride. Here is the typical working. And just to point out that this extra conversion from volume of oxygen gas to moles of oxygen gas involved rearranging the ideal gas law constant. The balanced equation tells us it's 2 moles of potassium chlorate for every 3 moles of oxygen. And then finally, using the molar mass of potassium chlorate allows us to calculate the mass of potassium chlorate. Again, these stoichiometric problems are just like any other stoichiometric problem. Essentially, things need to be converted to moles, either because you have a mass, because you have a volume of solution, or you have a volume of a gas. And in each situation, it's just a slightly different sort of conversion to convert those quantities to the moles, and then using the balanced equation, the coefficients, etc., we can find out about another reactant or about another product. I hope this video has helped you sort out how to apply stoichiometric approaches to balanced chemical equations where at least one reactant or product is a gas.